Hi, and welcome to our 117th test and measurement video. The subject of this series of videos is electronic measurement and display instrumentation, ranging from the electrician's simple test light, which indicates presence and absence of voltage, to some far more sophisticated devices, such as the oscilloscope family of instruments, including the spectrum analyzer, waveform analyzer, and vector scope. Many of them have liquid crystal flat screen displays, replacing the old cathode ray tubes, and associated alphanumeric readouts, which represent electrical parameters to an impressive number of decimal places. The displays show us what we are looking at in lovely graphs, while the numeric readouts quantify volts, amps, and so on. For many applications, we may have to know the degree of precision in these measurements. This line of inquiry becomes somewhat complex. The fact is that there are substantial differences between resolution, accuracy, precision, and what we think of as correctness. Consider, for example, a digital voltmeter that begins at 0 volts and extends to 1,000 volts, with a digital readout that displays the number of volts in steps of 0.001 volt. The resolution then is a millionth of a volt, but the accuracy is unknowable unless there is an external standard to which it can be compared. Resolution can be expressed in terms of number of decimal places or parts per full-scale reading. Accuracy, in contrast, describes how closely the reading corresponds to an ideal true value. This presupposes either knowledge on our part of the true value or, at the very least, possession of another instrument having greater resolution and accuracy. We quickly get into an infinite regression into ever smaller increments, eventually encountering the quantum divide, where indeterminacy is the governing principle. In our world of classical measurements, the whole thing is a little more accessible. To illustrate, let's do some measurements with real-world electronic instruments. Here is a good way to connect meter probes, especially when there are 2 or more conductors that have to go together. Solderless connectors, so-called wire nuts, work well because then you don't have everything jumping around. For a voltage source, we're using a Tektronix PWS4305 programmable DC power supply. A good feature in this instrument is its graduated output, adjustable from 0 to 30 volts using the knob or keypad, which means that you can apply power to the device under test gradually, so that if there is a fault, it shouldn't be catastrophic. I've set the power supply output at 12 volts, and it is connected to this Fluke 8808 5.5-digit bench-type multimeter, which incidentally has a 4-wire Kelvin-type ohm meter for doing very precise low-resistance measurements. Its inputs are rated at 300 volts, and the overall instrument is rated as safe for up to 1,000 volts in Cat 1 electrical environments and 600 volts in Cat 2 electrical environments. Using the wire nuts, I simultaneously connected the power supply to a Fluke handheld multimeter with 1,000 volt Cat 3 and 600 volt Cat 4 ratings. Let's see what we get for readings. With the DC power supply putting out 12 volts into a maximum 1 amp load, the bench-type multimeter reads 12.0020 volts with a 4 decimal place resolution, and the handheld battery-powered multimeter reads 12.002 volts with a 3 decimal place resolution. This drops down to 11.9993 volts DC and 12.000 volts DC respectively. All three instruments have warmed up to over half an hour, so the readings are quite stable. As for accuracy, with the information at hand, we cannot give an answer. A definitive determination of accuracy would presuppose an ideal perfect voltage source. Thanks for watching. New videos are added periodically, so check back frequently.